Hey everybody, I noticed recently that one of the things we kind of struggled with in class was telling if a function was linear or nonlinear. So I just wanted to kind of clarify how that works. So when you guys were in seventh grade, you should have seen a handful of different types or different forms for linear equations. So that was slope-intercept form, point slope, standard form. I have them all up here. Keep in mind that the m that you see in slope-intercept form and point slope, that m represents the slope. When we have the b in slope-intercept form, that was our y-intercept. If you were looking at point slope form, that y sub 1 and x sub 1, well, x sub 1, y sub 1 is an ordered pair that would be on the line. And when you looked at standard form, the stipulation was that a had to be a positive integer, positive whole number. So all of those, hopefully you remember, made lines, or when you graph them, they would look like a line. Keeping in mind a linear equation, it has that word line in there. So if you're looking at a linear equation, it should be a line when you graph it. And then you guys also had seen horizontal lines and vertical lines. So horizontal lines are technically still in slope-intercept form. It's just that the slope is 0. So if it was y equals 0, x plus 5, I can really just write it as y equals 5 because 0x is just 0. So that's still technically in slope-intercept form, but then the vertical line is a little bit different. Remember, vertical line going up and down has an undefined slope. So that one doesn't fall into any of the other categories we looked at. So you guys definitely should have seen all of that in seventh grade. And then in eighth grade, we did talk a little bit about linear functions, and we had a unit where we were looking at linear functions versus exponential functions. So just as a quick reminder, the exponential functions would have looked something like this, where you had your starting value times the common ratio raised to a variable. So we said that that was exponential, and when the other ones, we knew that the linear ones formed a line. We said that exponential functions formed more of like a curve shape. They made more of like a J curve, I called it. So that should be a nice review of what you guys saw earlier this year. And you might notice again, this one that we talked about that's exponential and nonlinear, it has a variable in the exponent. So it's interesting. So I'm going to go now to my online graphing calculator. I'm using Desmos. If you wanted to try any graphs on your own graphing calculator, you could. I'm just going to use Desmos so you can see it. But just as a quick reminder, say I graph something in slope-intercept form, it makes a line. If I do something in point-slope form, it makes a line. If I do something in standard form, it makes a line. And if I do the vertical line, or horizontal line, all of those make lines. So if I look back at the equations, they all make lines. And what's funny though is if I went back to my equation that I said was nonlinear, we said the problem with it was that it's well, not problem, but something about it that made it be exponential is the fact that there was a variable in the exponent. So I just kind of want you to like ask yourself, if you look at all of these equations that I just graphed, what do you notice about exponents here? Like if you looked at any exponents, do you see any? If you don't see any, what does that mean? Please keep that in mind. So like if on the 1, if I don't see an exponent, keep in mind that would be y to the first. On the x, since I don't see anything, that would be x to the first. And if you look down the line at all the equations, all of them just look like y or x. So they all really are x to the first or y to the first. So we said again that when we had variable as an exponent, it made it be a curve. And maybe we'll just try a couple other ones. So if I had a variable as the exponent, it's a curve. So there's another one. Again, it comes out to be, oop, type that in funny. It comes out to be a curve. So what if it's not a variable though? What if I just have like x to the third? That's not a straight line. Or if I just have y equals x squared. Oh, that's a U shape. That's not a straight line either. Interesting. Maybe what if I stick like a negative in front of it? Oh, now it's still U shape. So then we're seeing that those with the x squared and the x cubed, those are not linear. Those are not linear. Say, what if I tried it and I made it negative? Oh, that's not a line either. So hopefully what you're noticing is as soon as you have a exponent as a variable, that's something other than 1, see, and keep in mind right here, I don't see anything, so that means the exponent is 1, but as soon as I have a exponent other than 1, it's not going to be linear anymore. Even if you do a negative exponent, if you do 2, any exponent on a variable other than 1 is going to be nonlinear. And I just wanted to mention there's one other pretty famous graph that's going to give the same thing without the exponent, and that's going to look like the absolute value graph. So that makes like a V shape. I always remember it makes a V shape because absolute value starts with V. So no matter what, as long as you have absolute value in there, it is going to be a V shape. So that's not linear either. And then one other thing that I wanted to clarify, when we mentioned the negative exponents, something like this, or say I had like y equals 2 times x to the negative first, that technically is the same thing as that. So just please keep in mind those are equivalent. So even if you see like an x in the denominator, that technically is a negative exponent. So keep that in mind. But then again, if I do just no exponents, it's going to make a line. All right, hopefully that was helpful.